will be presented by Amelia Anderson, and she will help us to recall principles of Bohr theory, which is behind atomic spectroscopy.
Yeah, so like you said, my name is Amelia, and I did my project on the 2D rotation of Bohr model for non-equilibrium orbitals. Some of the equations I used this first equation, which converts angular momentum to polar coordinates, so we could plot the angular momentum in a way that we can understand it on the Bohr model. And then the second equation is it shows the difference between kinetic and potential energies and how they're related to the Hamiltonian. My methods, I used a MATLAB code written by Dr. Killen, and then I added the commands to automatically save the videos so I could upload those to YouTube later, so I can add them to my presentation. I changed the numbers of nodes and then reran the code so we can see how the nodes changes the angular momentum of the electron movement, and then we analyzed how those nodes affect the movement. So here is just a polar standing wave, and the red line on there, they're all kind of overlapping, but just imagine with me, and we'll see them on later plots. The red line is the real part of the wave function, and the green line is the imaginary part. And then the blue line is the combination of those, which is the red line squared plus the green line squared and the absolute value of that. And then the blue line shows the stability of the electron in each node and orbital. So if the blue, later in the videos, if the blue line is pretty much unmoving, then the electron is going to be more stable. And if it's moving, then the electron is not stable and will quickly change so it will become more stable, and then it's less likely to undergo a transfer to a different node. So here's the first node. I ran it with 1.56 nodes, and you can see the very quick movement of both the red, green, and the combination of the two in the blue line. So when there's not an even integer number of nodes, then the electron is a lot less stable, and it's going to try to get back to a more stable state. And then the second one, we did 2.02 nodes. So clearly those movements are a lot more stable, and the combination of the red and the blue the red and the green makes the blue line unmoving. So this electron is pretty stable in its condition. And then moving forward, here's 2.64 nodes, and this is unstable once again because it's not an even integer. And then finally, here's 3 nodes, 3.01 nodes, and this is stable once again, and that blue line is unmoving, so it's happy in its current position. And then, so conclusions for this project was as the number of nodes change, the radius from the nucleus increases as the number of nodes increase. If we go back and just compare the radius of each of these, it clearly gets larger as we move forward, and finally the largest at 3 nodes. And then, yeah, as I mentioned before, the even integer values create smoother movements and more stable atoms. And then the value of orbitals is 2 times the number of the nodes, so there's 1 positive and 1 negative for each node. And then finally, we looked at limitations of the Bohr model, so it's only a 2D model, so it can't show 3D movement, and that led to the lack of understanding of what the electron would do in a 3D space. Some references in there.
Okay, thank you, Amelia. Then the presentation is open for discussion.
So in your conclusions, you said that you need an integer number for the nodes, right?
Yes.
So in other words, you need to quantize your momentum, your angular momentum should be quantized,
yes.
Right? And this is very valid, of course, statement, which you proved. However, you didn't show the results with 300. You were showing 301, 2 point something.
Yes.
Was it is it an issue to get exactly the even number for your code? Or you just didn't show it to us? Because it's not interesting.
Well, there's that. But the code did not run as well with completely even integers. We wanted to have 3 significant figures in each value of the nodes. So we just ran it not completely equal, but we got it as close.
So in other words, there's some bug in your code which not allowing you to really get exactly integer number.
Yes.
So there's maybe some numerical errors which
Yes.
results that you need kind of a little correction, and you cannot really get the exact even number.
Yes.
More questions, please.
So, can we use this simple picture that you got to understand any no observation in experiment? Yes, any simple experiment that some experimental data where we can use this picture to understand?
I mean, you could use it in a multitude of different experiments if you're able to. This is kind of atom by atom, not the complication of a molecule. So, yeah, the blue line just, if it's stable, then the electron is going to be less likely to transfer. But if you're looking at an atom where the blue line is moving all over the place, then the electron is going to be more likely to transfer. And we just, well, I looked at it as...
Electron is more likely to transfer from the atom.
Yes. Or move to a state where it can be more stable within that atom.
But can you really give some example of the experimental evidence of something like that?
Is there a connection to
Some experimental
hydrogen atom?
evidence of the Bohr model.
I did not look into that.
Come on.
You can.
What exactly is the reason why Bohr created his model? There was very clear need from experimental side why he really started working on it. And how he proved that his model is right.
He looked at
Let's go to your questions. Maybe they will help you. Yeah. So your last equation, what does it tell?
at the values of even integers of nodes, the don't exactly know.
So what is H?
Hamiltonian.
And which observable, which dimension it corresponds to? Like momentum, position, or starts with letter E?
Eigenstate.
Observable, eigenstate of Hamiltonian, but it can be kinetic or potential.
Energy.
Yes, good. So if you plug in the quantized values, or if you look that you have integer number of nodes, what will be the values of energy from this Hamiltonian equation?
Would you get different energies for different values of your quantized L? And how is it changing? If L grows,
And the Hamiltonian grows.
energy.
Yeah.
So
Energy grows.
Mhm.
And because L is quantized, then what happens with energy? Like L cannot take something in between because then your atom is not stable.
Mm-hmm.
Then you really need to take all integer numbers for L, right? Then how does it affect the energy? Does energy continuously changing when you
or it takes only discrete values.
Takes only discrete.
discrete values which depends on this L, right?
Mhm.
And now go back to experiment. How does the hydrogen, the spectrum of hydrogen atom looks like in the visible range?
It's very discrete values.
Actually, there are 4 discrete lines,
Mhm.
right? And this was kind of a main puzzle. No one could explain before Bohr. Why is it discrete? Why is not kind of a distribution like you see from the black body radiation, which is just spreaded kind of distribution in over all energies, right? And this exactly explains if you have one single electron in a hydrogen atom moving from the ground state to the first equilibrium, first, second, and so on excited states, right? Results on the discrete energies. If they go in a visible range, you really can see them just by eye. And this is evidence of this model. It works. He was able to use this model and predict these energies, which then were compared with the hydrogen atom spectra, and they looked very nicely there. I'm not sure whether you were thinking about this experiment.
You know, people propose a model for purpose. They was trying to understand something, and usually it comes from experiment.
Yeah.
So that's why I wanted to see the next.
Right. More questions? Morgan? No? It's not questions, it's applause. Okay. Well, thank you, Amelia. So we have 2 more presentations. Steven will be the next. And his presentation will be very much different from anything we heard before, and very much different from anything you may have heard in the previous years of this class. So instead of looking on either electronic or nuclear degrees of freedom, he will look onto spin degrees of freedom.
Hi, my name is StevenWestra, and as Dr. Killen said, I'll be talking about spin degrees of freedom.
We cannot hear you.
Oh, sorry.
Talk a little bit
Do
louder.
you need to launch the presentation mode?
Oh, right. You can't tell, I'm a little nervous. All I've had to eat today is coffee. So,
You can take, if you are not in the good mood to speak over.
hello? Yeah. Can you all hear me now? Yes. Yep. So, my name is StevenWestra, and as Dr. Killen said, I'll be talking about spin degrees of freedom in electrons, and specifically the free induction decay of electrons from magnetic moments in NMR. So first, we're going to have to cover some theory, since as he said, mine is very different from everyone else's. And that would be, what exactly is spin? And that is a very hard question. If it wasn't, I'd probably have no real problem with it. So it's an intrinsic property of electrons and other fundamental particles, which doesn't really tell us anything. It's more accurately, it's a form of angular momentum of a particle. Probably the analogy, it's a ball that's spinning, except it's not a ball and it's not spinning. So then what is it? Well, specifically, the spin number of an electron is the eigenvalue of a wave equation for the k number of states where the wave function is an eigenfunction of s hat z for the summation of k terms of s hat z k. That would be the basically the z value for a vector of magnetization, basically. So that allows us to see that they'd be represented by a sphere, basically. That would be a block sphere. Well, what is a block sphere? It's a geometric representation of a qubit where the poles of the sphere represent the 0 and 1 states. More usefully, it's a way of visualizing the magnetic vector of a spinning electron as it moves through a magnetic field. So we have our magnetic vector is equal to g summation of k of the sk of time t, where the sk is the combination of the x, y, and z components of the vector, which are controlled by these equations, which I will show later. So, now what is a spin echo? So as the magnetic moments of a group of electrons move around a block sphere around the equator, that at one point in time they will synchronize and constructively combine their signals into one very large signal. Now, the exact time that this happens for an atom is unique to each atom and to each electronic environment, also how it's bonded for every single state that there can be. This is the principle behind how NMR spectroscopy can differentiate elements and atomic structure this way. And now we have a very, very messy graph. So what's happening on this graph is that all of our electrons in the magnetic moment, in the ensemble, start at the same level. The pulse, the half pi magnetic pulse that brings the electrons from the poles of the block sphere onto the equator, which is represented by these two lines, at which point the varying individual frequencies that they move around the equator, which is dependent on their individual electronic environment, cause them to diverge into these various purple and yellow-orange lines until they reach the pi pulse, which flips them 180 degrees in the sphere. And as you can see, that changes the way, so that now instead of diverging away from one point on the sphere, they are now on the opposite side, converging towards a separate point on the opposite side, which is represented here and here. And so we have two identical signals, despite the fact that they are now in different places in time and space. And so a more useful visualization, if you can't really wrap your head around that, we have our electrons here at the top of the block sphere, which are then moved to the equator by the 90 degree or half pi pulse, so that they are now in the xy plane of the sphere. They then proceed, the various electrons, since this is more than one, move in various ways around the sphere at different rates, and that's such they counteract and destructively combine to reduce the total of the signal that you would see. This is until the pi pulse is received by them, at which point they flip to the opposite side of where their positions were originally on the sphere, and they now begin to converge to a single point on the opposite side of the sphere. So, a nice thing I got from Wikipedia shows this in a smooth motion. And you see that at one point they converge on the opposite side and form a new signal, even though there shouldn't be any magnetization present. Now, what did I do exactly? Well, as the electrons move, they move at different rates. Specifically, it's called the disorder is the variance between each individual magnetic moment as it moves. So, stated earlier, they are defined by the summation of the x, y, and z coordinates, which are defined by various differential equations. The important variable in this is the plus or minus I delta omega k. They do so at different rates. The difference between those is defined by the delta omega k. So here are the two electrons, the two formulas that I used earlier in the formula to define the magnetic vector. And here we have the delta omega k components, which are the important factors. So in the MATLAB code, delta omega k is represented as a multiple of omega. As you can see here, the original was 0.015, where this can be, x represents any value that would differentiate between the different speeds that they move. With x is starting at 0.01 in 0.025 increments up to 0.02. So what does that look like? So here we see the signal that you would receive on the block sphere, where as they move around the equator at different rates, they destructively counteract each other's signal until they converge at a single point, and we see a sudden surge in signal on the opposite side. Now, graphed to link to the YouTube video that Dr. Killen helped me put together, that I took that from. If we graph that, we see this sort of graph, where the orange and blue line combined represent the measured magnetic signal. Now, as you can see, as disorder increases, this is 0.01, 0.0125, 0.015, and increasing so on to 0.02, the width of the peak increasingly narrows the larger the disorder is between them. So this is very important, as the width of the peak is a limitation in the resolution ability of an NMR to distinguish different electronic states. So if we graph that as a combination of the area of the peak over the multiples of W, we see this very smooth sloping trend line as the disorder of the state of the magnetic moments increases. And it says T2. I'm sorry I did not define what that is. T2 is the relaxation time, the time that it takes for an electron that's been put through a magnetic field and been brought to the XY plane to return to its initial sort of state after it's removed from the electronic field. This value is different for every element and is part of the way that spin echo is used as a way of determining the state of the atom. So what happens if we make the disorder really, really large, like 7 times as large as the original one that we started with? And something very interesting happens. The total area of the peak completely breaks down, and it loses all symmetry. There's no symmetrical large peaks on either side. And what I'd speculate about what's causing this at this point is that the disorder is so large between each individual magnetic moment that they aren't able to immediately constructively rephase into a single point. By the time the first ones are rephasing, the other electromagnetic moments are still far around the sphere, and by the time the last ones are rephasing, the first ones have already returned to their initial values. Questions?
Okay, but thanks, Steven.
Now we're almost 10 minutes.
And presentation is open for discussion.
Yes?
You mentioned that this is kind of applicable to the NMR spectroscopy,
Yes.
but then you were also talking about, like initially, I think you said it several times, that you talk about spin of an electron. What is used in NMR? What kind of spin they use? Is it for electrons or for something different?
Might have confused some there. But the important part is that
it doesn't change the overall, how to say, physics and formulas which you were showing.
Algebraic processing.
In an atom, are there anything else which has spin, or it's only electrons which do have spin? What about protons?
All elementary particles and quarks have spin. However, in the nucleus of an atom, they are counteracted.
Is proton a fermion or not?
No.
A proton, a single proton.
Yes.
Proton is a fermion, right? But if you talk about nucleus, right, depends on whether you have even or odd numbers, and they might be not fermions. So in NMR, it's the same idea, but my understanding is that they talk about the spin of the nucleus, spin of the protons.
So in your talk, you can replace only one letter if you want to speak about electrons. Instead of NMR,
EPR.
EPR, yes.
Mm-hmm.
More questions to Steven? If not, then thank you once again. Please leave it here. So the next presentation is by John Swanson. So his presentation will be also very unlike and similar to anything you heard before. In recent year or couple of years, there was an interest to so-called two-dimensional quantum materials, and John was brave enough to try to apply skills from the course for exotic materials. Are you in a mood to speak loud, or you need to?
I'd rather you speak loudly.
Okay.
Hello, my name is John Swanson. I will be presenting on the correlation between eigenstates as the magnetic field is changed. So getting into that, just brief overview, not that people don't know what superconductors are, but a superconductor is a material which can move electrons from one atom to the next with no resistance. And so this is often researched on low temperatures, bringing metals down to low temperatures. They can become superconductors in many cases. But one area of research that maybe isn't as looked into or known about is the application of magnetic fields to form superconductors in metals. Because I know metals oftentimes, when they are superconductors, give off magnetic fields, but inducing them with a magnetic field may have a similar result to bringing it to low temperatures, if we look into that a bit. So, some basic methods of research. there's a MATLAB code that was used to do this experimentation. I'll get a little bit into what was behind that. And so through this, we took the eigenstates that were found through this code, and they were converted to density of states across energy. And then that was used to determine if a superconductor could be formed based on how the density of states reacted. And so some equations that were helpful in doing this. This first equation relates the Hamiltonian to energy in the eigenstates. And a lot of these are really intertwined, so actually doing this computationally may be incredibly challenging, which is why a code was used, because I'm not sure I could do any of this by hand. Second one, equation right here, we found, use the energy found in the first equation, and using the first equation to find the density of states. And then moving past that, this equation is used alongside this once this is solved, and it can be plugged back in, as you can see here. And then this is just an equation for the Hamiltonian, with L sub z being angular momentum, V sub z being magnetic field, and both of these are actually in the momentum space and not in any position. Yes. Thank you.
What is LU and HO?
Okay, so LU is the lowest unoccupied molecular orbital, highest occupied, and so for this one, lowest is calculated using positive, highest using negative. So, and so a little bit of a representation of this last code here. This cone is kind of what that equation looks like when mapped out again in the momentum space, and this ky and kx are represented as px and py here. And so the top is the lowest unoccupied, bottom is the highest occupied, corresponding to positive and negative. And then this over here is a material that this could be researched upon. So this is the top. This is the model of layered bismuth telluride, and it's just one of the lattices of that. And so this is something that the experimentation done could be done upon. Okay, so for the actual data, at the bottom here, these are the eigenstates across energy that were found through the experimentation. And above each of these is a corresponding density of states that were found when converted. So these first three, this is throughout the slides I'll show. This is as the magnetic field increases. And these first three are pretty similar. As you can see, this is the density of states of the holes where there weren't electrons in the lattice, and then of the electrons found. And the dotted line you'll see is the combination of the two of those. So nothing really too interesting here. As the magnetic field was increased even more, it started to see that there was a bit of a dip here, which started to grow, as you can see in that last one, almost forming a peak. And then finally, here we can see this is the strongest peak that was found through this experimentation. I'm sure it could be found stronger if you were to get to closer values, but this is what was found. And then it started to dip down. And so what was determined from seeing this peak in the density of states is that it is evidence for a superconductor. I believe you can look at Fermi's golden rule for showing that when the density of states increases at a specific energy so sharply, it could indicate that a superconductor is being formed. And so, again, it flattens out afterwards, but that is, as a magnetic field is increased, that is something that is known to happen for density of states. So that doesn't prove this is true, but it gives further evidence that this is reliable. And so this is just a video of all of those kind of mapped out, kind of what that would look like. Just for a little bit of a better visualization of the density of states over time. Okay, so some observations that could be made here again by Fermi's golden rule. We can claim that as density of states increase at one specific energy, that you could maybe see a superconductor being formed. And so further indication of this was found when looking at the eigenstates of the found through this experimentation. And so I'm not going to show all of them because there's a lot, but I picked a specific field. So when the B field is 0, I believe this is the first eigenstate and the third one, according to our graphs on an earlier slide. There's relatively little to see here, which indicates there's little motion. And so as we move up in the magnetic field, this should be negative 2.33 times 10 to the negative 5. There's a lot more fringes here, as seen by the second eigenstate and fifth one, that's what I believe these two are. And the fringes should indicate that there's further motion within these eigenstates. And that continues up to negative 4 times 10 to the negative 5. And this is at a much higher energy and a much lower energy. But as you can see, there's a lot of activity going on there, which further indicates that there is motion, which would lead you to believe that maybe a superconductor could be formed under these conditions.
A second. So
Yeah.
this is just different eigenstates at the same magnetic field, right? You
No,
fix the
no.
strength, so
So-
you're changing it.
This is magnetic field is 0. This is increased to 2.33 times 10
Which is
negative
kind
5.
of optimal, where you really see
Yeah.
the formation of
And then the largest peak was seen at this one. And so this is at a higher energy, but this is as the magnetic field is increased. This is just a couple of the eigenstates taken out of that. And so observations, again, I said, as the fringes increase, that leads us to believe that there's an increase in motion. And there are the eigenstates, and my units are not quite great, but they're there, can't change them. And so basically what I took out of this is upon induction of a magnetic field, it could lead us to believe that a superconductor could be formed under the right conditions, which I think is something that's very interesting. So thank you. Questions? Yes.
Sorry, I'm one of the students in my question.
Oh no.
Well, you're ready to upload infinitely. Okay, Alyssa.
Can you go back to, just keep going, I'll take this out. Okay, right here.
Yes.
So on the first one that you have, why are the states less quantized as you keep going up? There's like obviously not like plateaus. Do you know like why it gets so weird? Or,
Like you mean with
nope, the bottom graph.
here?
Yeah.
Oh yeah, because they're not. So this dip. I know I looked into it at some point. I think it indicates a change in the motion, if I'm not mistaken. But I'm not entirely sure why it goes from, the tiers to that kind of steadily increasing pattern. I guess they're just because the eigenstates would probably be taking from different spots that aren't necessarily in one plane, because the eigenstates are kind of correlating to this conic shape. But I could be mistaken in that.
Great question, and answer is almost complete. Can you indicate our attention to magnetic field equals 0? And count how many degenerate eigenstates you see if you start from lowest.
Here?
Yeah, no degeneracy for the lowest. And next one, how many? How many? How many? 4.
4. Yes.
Okay, now let's go to your eigenstates at the very end.
I mean here.
Eigenstates, not
Oh, I see what you mean.
Yeah. So, can you explain how this degeneracy 1 and 4 relate to your eigenstates with 0 field?
So this is at 0 energy.
Zero magnetic field.
Thank you.
And
Zero
zero.
magnetic field. And so at the degeneracy of 1 and 4, you can see that both of these are, well, they're basically the same, at least in this, which indicates that both state there's little interaction, but not exactly sure that's what you're getting at.
Does momentum, he's on the right way. We will complete this thought, and thank you much, Alyssa, for great question. Is momentum changing or conserved in absence of magnetic field?
It appears to be considered.
Conserved. So if you create a state with very certain value of momentum, delta function of momentum, is there any mechanism to disturb it?
No.
No. So on your grid points for different values of momentum, keep this eigen. On any value of grid point, the delta function certifying very specific value of momentum will be an eigenstate because there are no reasons to change eigenstate. Right? And if you take square lattice grid points, how many nearest neighbors are close to point 0? You already answered, but let's focus on the back. This is 0 point. How many closest neighbor to this point along this grid lines? 1, 2, 3, 4. And all of them will have the same value of energy. Because it is proportional to the value of energy. So it's 4 degeneracy. And it will be spiked from state with 1, degeneracy 1, and degeneracy 2. Can you go back to your degeneracy images with magnetic field 0? And can you maybe, can you now repeat the same to Alyssa and pointing right things on the?
I can do my best. So here, momentum is conserved as we go across, and so the closest 4 are seen up here to. What was your question? Your question was more based on.
Your question was why it's so smooth.
Yeah, on this one. Rather than.
Well, and then it goes back to being like when it goes back to peak, it goes back to being normal again. I guess I was just wondering if there's like
a reason why it goes from. I get exactly what you're asking. Why it goes from the tiers to kind of a more curved pattern and then back to the tiers again.
Because of the discrete nature of grid points.
Okay.
So it could be a numerical artifact. If we take finer grid points, it may disappear. More.
Yes.
Can you get back to the slide with a picture of bismuth telluride?
Yes, for sure.
So bismuth telluride is a narrow bandgap semiconductor. Bandgap is about 0.1 something. So on the left, you show something which is more like metal, more like graphene. I don't see any bandgap. So do you think that your model on the left can be applicable to the material on the right?
I think a similar model might be, but maybe not this specific one. This was more of an example of something that has been used with superconductors that this may be able to be applied for, because I know this has been used to insulate in quantum computers with just some research that has recently been done. But I'm not sure if this exact model would be applicable to this.
I mean, the whole idea is you can use magnetic field to manipulate the electronic state in the bandgap region. So, okay, then that's it. Okay, my question is very simple. Do you know of any example of real material where they observe, superconductivity by applying the magnetic field?
In my research, I could not find anywhere that this was observed in any material, but this was more just to show that maybe it could be found to be applied to some material, but I could not find any evidence of the material that has been shown to have that functionality yet.
Have you seen an opposite effect when increase of magnetic field limits the conductivity? Like your regime when you keep increasing it to higher values?
Well, eventually, like if you look here, as the magnetic field is continually increased, eventually it does start to
it lowers the conductivity.
lower the conductivity.
This is very standard effect observed in experiment. So half of these results agree with experiment.
Okay, that's good enough.
The other half is more the part that would be interesting to put further research into based on this evidence.
No, something to keep in mind is, when you had the enhancement of the electronic studies at the Fermi level, it may lead to superconductivity. But yes, it doesn't mean that if you had enhancement, yeah, you have to have a conductivity. Right? You may have it.
Yes.
Okay. Yeah.
It's necessary but not sufficient.
Yes, right.
More questions to John?
I have a general question which is kind of related, or I would say the answer to my question was already answered in a question from Hoang. And so technically this bismuth telluride, right? So it's referred to the so-called Dirac materials because it's not small semiconductor, it's a Dirac materials, means they completely close the gap at one point, right? And what other materials do you know which behave in the same way?
Well, that's a wonderful question.
And anyone from audience may help to answer this question if it takes longer time.
I do not know of any names directly.
You should.
I should.
This is very common material. I would be very surprised if you have
in the
never seen
layers?
it.
Because I know graphene works in
Yeah, this is one. This is the most common one, right? So, but there are of course more than one material like that. And technically, the computational chemistry was applied to create some kind of a predictions or database. They tried to go through many variations of possible semiconductors of multiple combinations, metal, non-metals, rather, and calculating electronic structure, the dependence energy on the band, on the K points, and checking whether you can get the Dirac materials or not. And yeah, we found about hundreds of materials as predicted. Some of them not synthesized yet.
More questions to John? If no, please join me in and last note that probably all visitors will agree that it was a successful presentation. Please submit if you did this form, and class attendees can also do this. So the exposure of class attendees to unbiased problems was a chance to practice your knowledge in more real life environment, and there is a hope that it will help to keep part of the knowledge more long-lasting in your memories, and it will eventually help in in other classes, like inorganic, PChem2, computational chemistry, which all you are invited to take, and in your academic, teaching, or industrial careers. With this, let me thank all speakers and participants of the discussion. Yes.
So may I just make a comment, because I was coming for, Dmitry is teaching this course for about four times already, right, for 3. Anyway, I was coming for this presentation of students from previous years, at least 4, I think it was 4 times already. And I really was amazed with your presentations as a group, because usually, yeah, there are of course good presentations, very good presentations, but there are really presentations which are kind of very weak and people don't know what they do, we don't know how to ask questions. I was very, very pleased to see that how many 8 people who were presenting really showing very, very good understanding, level of understanding was very high, and overall presentations were just interesting to listen to you. It was interesting to see what you were doing. So really, I think as a group, every of you was really, I don't know, I'm very excited seeing your presentations. Really great work, guys.
Okay. And with this, meeting is dismissed, and class is complete.
So I think, I just say that I fully agree with that. I'm really impressed with you guys' presentation skills. It's much better than the other events that I Yeah, be proud of yourself. Yeah, lots of improvement. In
We are proud of you, for sure.
Yeah. Great job. Yeah.
Dr. Killen, you have some.
Yeah, so you just keep it as it's like.
No, I mean, comments like
It's fancy, but you just keep it off because for whatever reason, like it builds up steam and it like drips out the side. Like, yeah, so it's like it's stained. So if you walk in the class, it's like it's got like hot coffee.
Seven of us?
What are we gonna take?
Nice to meet you. Let's go.
It's slowly working on
What is your deadline?
It was 7, but I consider 8 is my number.
oh, you're going
Ooh, I love it. I love it.
But really, great presentation.
Yeah, they're all.
Yeah, this is good.
Thank you, Dr. Hoang. I really appreciate your support.
The code.
Also, I have an answer to your question.
Oh, yeah,
There's like,
so-
well, you were asking about the differential energy curves, and there's parallel and perpendicular energy. So one of them has like
I haven't.
so like that's how it works. So it was in my previous I was like it's just searching. It's like it's yeah, it's just like how yeah, and an entry point here like jumps like sideways or goes up the same yeah. It's a transition. So I had it written down and I had it all laid out, and then I couldn't get it to work the way I wanted it to. Yeah, well, I never got started. I started trying to it's something which is like a dye, because I wanted to show like the reaction between that and so it's like a dye that dyes it's just I was trying to follow it, and it was way too complicated. So I took a step back and do a secondary.
What is it trying to reach?
You can manipulate it.
Yeah, I think yeah, it wasn't my first.
Well,
but it wasn't like a bad.
Yeah.
Well, I'll see you next semester. Because you're teaching